In this video, we describe 3 common errors related to correlation. This is learning outcome number 4 for lesson 10.1. The first common error is assuming that correlation implies causality. Just because 2 variables are correlated does not mean one variable causes the other. For example, that Nobel Prize data that we were looking at, we saw that the number of Nobel Prizes that were awarded in a country was correlated with the amount of chocolate consumed in that country. Now, chocolate consumption cannot be assumed to cause people to win Nobel Prizes, nor would it be wise to assume that winning Nobel Prizes causes people of your country to eat chocolate. There's no cause and effect relationship there, but we can say that as chocolate consumption goes up, Nobel Prize winning goes up using the data set that we have. Now, we also, in that case, we're not certain that we had a simple random sample, so that should be considered as well. So we never want to assume that just because 2 variables are correlated that one of them has caused the other, because that's not necessarily the case. Often it is the case that 2 variables are correlated to a lurking variable, and that lurking variable may explain the cause of one or both variables. There's another one that's very similar to the Nobel Prize example. It's one that I've heard many times over the years. I don't actually know if there's a study backing this up or if it's just fictional, but I remember hearing about a correlation between ice cream consumption, similar to chocolate consumption, and the number of crimes or burglaries or something like that committed. And I don't think if we said that those 2 variables are correlated. So as crime goes up, ice cream consumption goes up. And as ice cream consumption goes up, crime goes up. Now you might think that those are causally related. That would be an unwise assumption to make, because eating ice cream does not cause people to commit crimes, and neither does committing crimes cause people to want to have a little ice cream. Those are both correlated with the third variable, which our author Mario Triola refers to as a lurking variable. That lurking variable in that case, for that example, is the weather. When it's warmer outside, people are more likely to commit crimes. And when it's warmer outside, people are more likely to eat ice cream. So the fact that ice cream consumption and crimes are related does not mean that either one of them are explained by the other. If you had a whole bunch of people in a very cold place eating ice cream, there wouldn't suddenly be an uptick in the crime rates. People still would commit less crimes because it would still be cold outside, because that lurking variable, that third variable, was not affected by the fact that there was more ice cream being consumed, for example. So we never want to assume that correlation implies causality. We can just assume that when we have 2 variables that are correlated, there is a certain relationship between those. So one of those variables can be used to predict the other, but it does not mean that one is actually causing the other. Another common error related to correlation is this. You don't want to use data based on averages, because if you use data based on averages, you're more likely to find a correlation when there actually isn't one. When you compute averages, or means, in other words, arithmetic means, what you're doing is you're suppressing individual variation. So as you look at samples and then you compute the means of those samples, all of the variation that was contained in that original set of data is lost when you compute the average or you compute the mean. So if you're using these average values, and then you're seeing if these average values are correlated with some other variable, it might seem that the averages are correlated with another variable, and the averages themselves may be correlated with another variable, but that does not mean that the original values were correlated with that other variable. So you want to be very careful about that. You probably don't want to use averages if you're trying to show that one variable is correlated with another. You want to go back to the original data set rather than using averages of that variable. And then the third error, excuse me, is ignoring the possibility of a nonlinear relationship. It's very tempting, especially as we get used to using technology, to just do the data entry and then assume that all the requirements are met, then look at the R value, look at the critical values of R or the P value, and then immediately come to some conclusion about a linear relationship. You don't want to ignore the possibility that there may be a nonlinear relationship between those variables. That's why it's really important to examine that scatter plot, of the data to see if there's a nonlinear relationship. Because if there is one, that could be potentially very interesting and very insightful about the relationship between those variables. The number crunching for the R values, the critical values of R, and the P value may show that, or may imply that there is a linear relationship between the two variables. But that linear relationship that is implied by those R values may not be the best may not be the best relationship between the variables. It might turn out that the variables are related in another way. They're not just related linearly, they're related maybe exponentially or logarithmically, or through a quadratic function or a polynomial function or something like that. So make sure you look at that scatter plot, and that way you will be sure not to miss any nonlinear relationship that may be obvious when you are looking at a graph of the data. So those are the three common errors. Remember, correlation does not imply causation. Don't use data based on averages, because then you may see correlations that aren't really there. And you want to be careful and make sure that you don't just do some number crunching and assume that the values of R and the P values are going to tell you the whole story. They won't. There may be a nonlinear relationship. And that's why it's important that we look at the scatter plot of the data before we even get started there.